Okay, so we've taken light. It's reflected off the object. We've taken it out of the eye through those subcortical structures, and it got to the visual cortex, our first level of higher level processing, or cortical processing up in the cortex. And we actually started discussing the visual cortex when we started talking about those feature detectors. This is a reiteration of those simple cells, complex cells, and end-stop cells that Hubel and Wiesel discovered. I went through and gave examples of each, so hopefully they make sense that we have particular neurons that are responding to particular orientations of lines or bars out in the environment. We have other neurons, the complex cells, that are responding to a particular orientation of line with a particular direction of movement. And then we have end-stop cells that respond to really the length, angle, orientation, and direction of movement. So as we've seen along the way, neurons are not just responding to light, and not to absolute levels of light, but they respond to some patterns of light and not to others. As we move farther from the retina, those neurons are going to respond to more and more complex stimuli. We've already gone from center surround, just those little dots, to lines of different orientation, moving in different directions. But we want to put that together. Those are still features, right? And we want to put them together into thus being able to see people's faces and the desks and the chairs and the couch and everything in the room. One of the things we're going to do before we move on from this kind of idea is to establish a link between the firing of those neurons and the experience of perception. And I think in this day and age, in the modern world, we think, of course, we see neural firing and that is being correlated with perception, and we all kind of know that, but we know that because of the research that has been done historically. So I'm going to go through a couple of different ways to answer this question of, do feature detectors, do those neurons and what they respond to actually affect perception? Okay, and the first kind of study is a selective adaptation experiment. And this is a psychophysical procedure where we're going to ask people, what is the smallest contrast that you can still see in these grading patterns? So when we talk about adaptation, what this means is that we have a decrease in response with prolonged exposure. We know that with neurons, the longer they are responding to something, they are fatiguing, and so their firing rate is going to gradually decrease, and we see a weakened response to a repeat of that same stimulus after they have adapted or fatigued. And we can use this information, we can use this kind of selective adaptation as a tool to study mechanisms of perception. So a selective adaptation study looks like this, and this is an example, right? We're going to do this with vertical lines, oblique lines, horizontal lines, all kinds of lines. I'm just going to give the example of a vertical line. So we're going to present a vertical line. Neuron X, which is tuned to vertical lines, is going to fire. As we continue to make presentations of the vertical line in that particular part of the visual field, the neuron X is going to fire less often due to fatigue. Okay, we know this happens, and the question is, do these feature selective neurons affect perception? If so, then as I'm adapting that neuron to that feature, we should also selectively see a decrease of the ability to perceive that feature. The stimuli they use for examining this question are these grading patterns, and we can vary the contrast. So you can see in the left-hand image, the left circle has a high contrast. The black versus the gray are very different, and the right-hand circle has a lower contrast. And the question is, how low can I get that contrast before you really can't even see the horizontal lines at all? And you're basically guessing at what orientation you're seeing. We can also vary the orientation. So as I said, I gave the example of vertical lines, but we could use horizontal lines. We've used oblique lines so that we can look at this selective adaptation of these various orientations of line. And when we look at the grading patterns, a particular grading's contrast threshold is the difference in intensity at which the bars can just barely be seen. So we're looking for another kind of absolute threshold, but in this case it's contrast. So if we go back to the left-hand image, we are lowering the contrast from the one on the left to the one on the right, and the circle on the right, if we kept lowering that contrast, again, there'd be a place where the bars could just barely be seen, and then you'd go into a place where you can't see them. And so we want to know, what is your contrast threshold? So the study looks something like what is on the left. If what I'm looking at is the question of these vertical bars and neurons that are responding to vertical lines, then what we do is we start by measuring the contrast threshold at a number of orientations. Okay, so vertical, various oblique lines, and horizontal lines. And then we're going to have somebody adapt to a high contrast grading. So they're going to look up at a fixation cross. We're going to have the grading, maybe they're looking right at it, maybe it's in a different part of the visual field, whatever, it's going to stay there. And as that person continues to look and look and look, the neurons that are responding to that grading are fatiguing, right? So they're adapting. And then after they've adapted, we go back and we remeasure all of those contrast thresholds to all of those orientations as we did above. And the expectation, right, is if feature detectors affect perception, then in this case, it should take a higher contrast for me to be able to see the vertical bars, because my those neurons have fatigued to seeing the vertical bars. And the results are off to the right there in those figures, and you can see the adapting orientation, this kind of increase in contrast threshold. How much more contrast, how much more did we have to get towards black and white before the person was able to see the vertical bars versus these different orientations off of vertical. And if we treat vertical as 0, we get off to 20 degrees, off to 40 degrees. If we're really within 20 degrees, we see a drop off, but we still have to increase the threshold to some extent, because remember, if you go back to that slide that shows the simple cell responding to the vertical bar, that it is responding to those oblique lines that are not quite vertical. Actually, so that's what's shown in the right-hand side. I'm sitting here trying to imagine it because I was going to tell you this. Surprise! This is it looks exactly like, or very much like, the original simple cell response. So the simple cell is responding really strongly, many impulses per second to the vertical bar. That's the one that needs the highest increase in contrast threshold. It's still responding to those within about 20 degrees, and they need some increase in contrast threshold. And as we get out to about 40 degrees, where that vertical bar neuron was not responding really at all, then we don't need very much increase at all in contrast threshold, or really none. I usually feel like I've thrown people into deep water here with the selective adaptation studies, so think about if I need to explain some of that again, or if you have questions, let me know. Other evidence that we have for feature detectors affecting perception, well, one is the oblique effect itself, and that we see this entire pattern of results where, one, we have greater sensitivity to horizontal and vertical patterns. We can get that contrast threshold lower and lower for horizontal and vertical bars than for oblique bars. We have more neurons coding those orientations, and we see a greater fMRI response in the striate cortex to those orientations. So we are seeing the response of the feature detectors themselves, and that playing out in perceptual sensitivity. Finally, there's one more way I'm going to describe how they looked at this question of whether feature detectors were actually causing perception, so whether those neurons that were selective to certain features were affecting perception. And this was called a selective rearing kind of study. This is from Blakemore and Cooper, 1970. And they looked at kittens reared in a tube with a singular orientation. Okay, so in this example in the picture, the kitten is, while the visual system is developing, the kitten is only experiencing vertical lines. So if I remember correctly, the kittens spent their time in the dark, except for 5 hours a day they were in this vertical tube. And I don't love the kitten study, and nobody ever likes talking about it much. I remember one of the researchers somewhere says, you know, the kittens seemed happy when they were in the tube and all that, but it just is what it is. Okay, because this is one of, back at this time, we didn't have fMRIs or these kind of sophisticated ways of looking at brain activity. So this was how they examined this question. So they're really looking at the role of environment on the development of those feature detectors. So as the visual system is developing, and I'm going to go ahead and go to the results, because I leave the picture on there. What you can see to the right in the B part of the picture is that a horizontally reared cat. So the cats had these those cones on their heads, and they could be raised in a vertical world or horizontal world. And because of the cone, they really couldn't turn their head and get different kinds of views of these bars. So they're really mostly experiencing, in this example, vertical, but maybe a teeny bit off as they move their head a little bit teeny bit off. So the horizontally reared cat, when we look at the neurons, the neural response, we see neurons responding to horizontal bars, and then as they get to different levels of oblique, we see some response. But you can see in the first part of B there in that image that there just are no neurons at all responding to vertical bars or bars that are even really kind of slightly off, 10, 20 degrees off from vertical. And for the vertically reared cat, they have neurons that respond to vertical bars and some of the ones that are slightly off, oblique, but they have no neurons that are responding to those horizontal bars. They also wanted to see this difference in behavior, right? Because we want to know, does this affect perception? So the kittens, they would test them with this either a vertical or rod or horizontal rod, and the kittens would pay attention to, if they were reared in a vertical environment, they would pay attention to the vertical rod, but not to the horizontal rod. So they would swat at it and avoid it, but at the horizontal rod, they didn't even seem to see it. They would run right into it. They wouldn't swat at it or react to it in any way. So we see a difference in neural firing, and we see the corresponding difference in behavior. Okay, I'm going to get a little bit of the way through, I think, this organization or mapping of the striate cortex. And I want you again to remember that with those feature detectors, what I'm talking about is the receptive field of the neurons. What are the neurons themselves responding to? And now with the organization or mapping, we're asking, how are those neurons organized in the striate cortex? Well, first of all, we have a retinotopic mapping. So we really, if you remember, we saw this at the retina, obviously, because it's in the name, but we also saw this at the lateral geniculate nucleus, and we're seeing it at the visual cortex. And this really allows for an efficiency of functioning, because neurons that are near each other, that have receptive fields that are near each other on the retina, are going to be near to each other on the cortex, which also means that the visual space, because you remember it's this flipped upside down image, but the visual space is, if something is close to something in the environment, it's going to be close to that. The receptive field on the retina, it's going to be close in the visual cortex, so it makes sense for putting information together as well. There is a slight displacement, but otherwise we have this retinotopic kind of mapping that gives us an efficiency of functioning. Second, we see a cortical magnification. So I have these put in this word art so that hopefully it tells you to look here. This cortical magnification is important, that we have our foveal retina. If you remember, we had that direct wiring of the cones, the kind of one-to-one wiring. Well, the fovea is taking up 0.01% of the retina. It's this really small part of the retina, but its representation in the visual cortex is more like 8 to 10% of the cortex's retinotopic map. And I'm going to show how this was determined through brain imagery and give you hopefully a better idea too of what this, remember, we've done this principle of transformation, we've done this principle of representation, what this representation that we now have is in our cortex, what this looks like. Okay, so we're going to look at a study by Robert Doherty and his colleagues that uses fMRI, or functional magnetic resonance imaging. And so that you know how they are getting this data, they are using magnetic fields, radio waves, and computerized enhancement. But that's what an MRI uses to map out brain structures. But for the functional magnetic resonance imaging, we want to see the brain activity. We're going to measure the oxygenation of the blood in the brain, and it follows this kind of logic. This is how it works: that hemoglobin carries oxygen. It also contains a ferrous molecule. So if you've ever cut yourself and licked it, I know that sounds fun, that it has this kind of metallic taste, has this ferrous molecule. So it lines up like tiny magnets when it's in the magnetic field. In these areas where we have high brain activity, first of all, we have blood flow to that area, and we also have the hemoglobin losing some of that oxygen because neurons are using oxygen as they are working. So this causes them to respond more strongly in that magnetic field. I have this slide that has a picture of somebody getting ready to go into the MRI. And I usually ask here if anybody's had the experience, because I think it's fun to share experiences and just to stop me talking. If anybody ever wants to share their experiences with an MRI, or getting an MRI or an fMRI, please do. I know I have plans for this Monday and we don't have a lot of time together, but it is an experience. It is a loud machine that is not a consistent loudness. It has a sound to it, and then every once in a while there's this bang, 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 clink, a clink, a clink, a clink, a bang, 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 and there's no, it always felt really unpredictable to me. The first time I was in the MRI was for a research study, so it was a functional MRI, but then they found a small cyst on my pituitary gland, and so I have to go in and get MRIs. And actually, I find it much more comfortable to go into the MRI without the weird thing on my face that's showing me, this computer strapped to my face showing me the stimuli that they want me to look at. And a lot of people talk about how really uncomfortable, if you have any kind of claustrophobia, and then the noise is going on, it can be uncomfortable. I don't actually find it very uncomfortable. Sometimes the studies are putting you in a position of going, this is weird. But I usually also really recommend here that you go and do the research, but I'm not sure how research is working right now, and I assume it's mostly surveys and not these kinds of brain imaging techniques, and the more the ones that are using our technology. But if you can, find one and go run an fMRI study at some point. What's happening in the fMRI, so when we're measuring brain activity, we really have to measure or look at the fact that we're looking at relative activity in areas of the brain. The brain is always active. So we are detecting these changes in the magnetic response of the hemoglobin, and we have to have some kind of subtraction. I talk about this as the subtraction method, where because the brain is always active, I need to subtract out some other activity. And usually what they do is they come up with a control task or a comparison task where they think you're not using the specific mechanisms or processes that are what I'm interested in my study, but the brain is still active, and so I'm going to have you in this kind of control task, and then I'm going to have you do my experimental task, and I'm going to subtract out the brain activity from the control task from the brain activity in response to the experimental task, and say that's the activity that is important for the processes that I'm looking at. Just so you know, I think it's really important when you read in the field, and in any field related to neuroscience or looking at fMRIs, to think about that control task and think about how much you agree with that as a control task, because that's sometimes one of the real questions of what are we looking at. as far as their brain activity and what processes they are doing in these tasks. I usually compare it to PET, and I've usually gone through the PET imaging and described it, but I've taken that out because he doesn't do it anymore, and this isn't, I don't think he talks about PET very much at all. If I need to, I will. But we prefer it to PET for a couple of reasons. One, there's no radioactive tracer, so people sometimes balk at being injected with a radioactive tracer, even though it's so little that it's not going to do anything. It also, but more importantly for most of what we look at, is it gives us a more accurate and detailed map than any kind of positron emission tomography. It's also less expensive. So with all of that together, the fMRIs are often the way we look at brain activity when we want to look at what's happening in a particular area or region of the brain. So Robert Doherty and colleagues in 2003 used the fMRI to determine the magnification factor in the visual cortex. And so they had participants look at a dot in the center. So it is on the fixation. It is where they're fixating, and it is then on the fovea. And then they had a stimulus light presented in two places, and they looked at the response of the visual cortex. And the two places were either near the center, so you can see that in A, in the red, it's within 5 degrees and very close to the fovea. I cannot remember now if I've said this in the class already. I think I did, but I'm going to repeat it here. When we are looking at visual angle, we have about 180 degrees of visual angle that we can see. Since our eyes are round, we do it on this kind of circle, but we're only seeing really half of the circle, right, as our eyes work. And so if we're within 5 degrees, we're pretty close to the fovea. Farther from the center, they get out past 10 degrees. That's that little area in blue. And what you can tell in the picture in A, that there's more. They're using more of the visual field there in the blue when they're farther off from the fovea. And if we look at the activity and the response of the brain, what they're showing in B is the response to the what's near the center. They're showing that in red, and then what's farther away, what we see the light in blue, they're showing that in blue. And you can see that even though that area that's near the center, that's near the fovea, is smaller, there's more of the visual cortex responding. And even though we have that area that's farther from the fovea, it's a bit larger, we have a smaller area of the visual cortex that's responding to that region of space. And this is a nice visualization. So if you look at where we look at it, if we're looking at, and this, I mean, getting information on our fovea is particularly important in reading. And so if we're looking at the word area, really, or we're going to foveate a little bit above that, but that's okay. So we're kind of looking between periphery and area, right? What you're going to see, so smaller surface area. If you look over to the rendition, the image of that over on the right, that is the A of area upside down. You can kind of see the word surface upside down and backwards, and then above that you see the little bit of the PERI of periphery. And as we get off in the periphery, and so it gives you this idea that we have foveal magnification. And if we're looking at what's actually what we're responding to in the visual cortex, it is this upside down inverted image with this magnification of really what's important to us and what we want, the more detailed information about. So it turns out we have extra cortical space for those tasks that also require visual acuity. So when we are looking at something and getting that more detailed information, we're looking at that because that task requires visual acuity. Good acuity is associated with a number of things. 1, a sharp focus of images on the retina. 2, that small amount of convergence of the cones. and three, a relatively large amount of cortex devoted to fovea. Okay, so my last statement here is that people with more cortical space devoted to the fovea also have better acuity. So if you remember Jessica saying those early events are really important, and what the textbook is really doing there is it is the importance of the early events in the visual system. So when we're at the level of the cornea lens and what's getting to the retina itself, but also that was talking about development. So what's happening during our development, and that all gets put together here in a lot of ways. It's important that we have a sharp focus of images on the retina. If you are like me and you're myopic, and especially if you started losing your eyesight before the age of 4, you didn't really have that sharp focus of images on the retina, and you're always getting new glasses to try and make that image sharper and sharper. But because that was happening when you were young enough that the visual system was still developing, you probably have less cortical space devoted to the fovea. So I usually tell this story, I'm mixing up my words, this story about my sister and I, where so we spend a lot of time walking outside. She lives on Edisto Island, and so we spend a lot of time just out in nature. I remember we were walking down the dirt road, and I said, I can't tell by the flight pattern. It looks like that bird is flying kind of like a hawk. Is that a hawk or is it a turkey vulture? Because they're far enough off that it's hard to tell one from the other. But it was kind of flying straight instead of doing that around and around the way that turkey vultures do. And she just kind of shook her head at me and said, you can tell by the beak on that bird that it's a turkey vulture. And I just kind of felt like I'm lucky to see a bird in the sky, don't you know? So she has really sharp vision of things that her bird was really far away. Clearly, she has more cortical space devoted to her fovea because she has really sharp visual acuity. And you can do that kind of comparison with your friends in your mind.